Welcome everyone, and thank you for joining us for this virtual presentation at MIPI DevCon. My name is Alain Legault, and I'm VP of IP Product at Hardent in Montreal. Today I'm joined by Joe Rodriguez, Product Marketing Manager at Rambus, and Justin Endo, Marketing and Sales Manager at Mixel. We will be talking to you today about an integrated MIPI DSI-2 display IP subsystem solution that can be leveraged for high-performance next-generation display applications, such as display for mobiles, AR/VR devices, and cars. At the end of this presentation, we'll all be taking audience questions. Before we go into details about our IP solution, let's take a look at what's happening in the display industry right now. So we put together this logarithmic charts to map out the evolution of display bandwidth over time for various types of applications such as mobile, AR, VR, and cars. So we can compare the evolution of display bandwidth against the increase in PHY speed over time. So we can quickly see that the PHY speed illustrated in yellow has not increased as fast as the display bandwidth requirement over time. There are not too many solutions to address this lack of bandwidth. You can either increase the number of transport lanes, which come at a cost, or you lower the bandwidth by using compression technology that has visually lossless video quality. We're now seeing more and more new products where the bandwidth requirements are getting even more significant. For example, in a mobile product, there's now a need for mobile to be AR/VR ready. There's foldable display coming and higher display resolution with higher frame rate. And AR/VR products, same thing is happening. There's higher resolution display at higher frame rate with larger pixel depth. And finally, for cars, there's now more and more display inside car, and each of the display at higher resolution to make a very demanding total bandwidth requirement. So given the market trend that I've just highlighted, there is a clear need to solve the gap that has emerged between the PHY speed and the display bandwidth required to create those cutting-edge display products. Fortunately, VESA DSC, a visually lossless video compression standard, was developed by VESA. The combination of visually lossless video compression, MIPI DSI-2 transport, and MIPI C and D-PHY has become an innovative solution to solving this bandwidth challenge, as you will see during this presentation. Before we dive deeper into each of the IP components in this subsystem, let's take a quick look at this block diagram of the proposed IP subsystem. You will notice that this diagram shows the host IP subsystem, and we'll be using this as our example during this presentation. But note that a peripheral version is also available. This is an IP subsystem designed to enable video transmission over a C and D-PHY. The subsystem includes support for VESA DSC compression over MIPI DSI-2 transport. We'll come back to this diagram later in the presentation, but first let's take a close look at each of the IP blocks that make up this subsystem. First, I will talk about the Hardent DSC compression IP, then Joe will talk about the Rambus DSI-2 controller IP, and finally Justin will talk to you about the Mixel MIPI C-PHY D-PHY combo IP. After this, we'll be taking a look at some concrete use cases for display applications. Before we talk about our IP, let me give you a very quick introduction about Hardent. So Hardent is located in Montreal, and we were the first IP provider to bring VESA DSC IP core to the market in 2014. Since then, our IP have been silicon proven since we have over 100 design wins across a wide range of industries. We've also been an active contributor to industry standard organization. I've been a member of VESA since 2013 and a MIPI Alliance member since 2015. DSC is a VESA standard that was released in 2014. VESA being the Video Electronics Standard Association. It provides an excellent picture quality known as visually lossless for bitrate as low as 8 bit per pixel. The picture quality is excellent for all type of content, natural images, text, and graphics. DSC is capable of providing such an excellent picture quality by using the combination of all these encoding tools that are listed in the diagram. Fortunately, DSC only requires a single line buffer of storage, which makes it compact while having a super low latency in the order of a microsecond. Since the DSC standard was released 7 years ago, several transport protocols adopted it into their standard, including MIPI DSI-2, which explains why DSC compression is now widely used in many consumer electronic products such as mobile, tablet, GPU, cars, 8K television, and so on. DSC supports all the important pixel format needed in consumer and professional application. That is RGB 444, YUV 420, 422, and 444, with pixel component size from 8 up to 16 bit per component. At Hardent, our IP supports both DSC encoder and DSC decoder. It is a soft IP that scales very well across a wide range of semiconductor processes. It has been used in cutting-edge processes such as 5 nanometer, but also in much lower ASIC processes and FPGAs. This IP is transport agnostic. It can work with synchronous and asynchronous data flow interfaces. In particular, our DSC IP supports all of the MIPI DSI-2 operating mode, video and command modes, as well as all data types. The IP interface supports all the important use cases for single and multiple video stream coming in and going out. The DSC decoder is error resilient and will recover quickly from a transmission bits in error. The DSC IP has been highly optimized for low power mobile application, frequency of operation for maximum throughput, as well as a low gate count for optimizing its cost. There are many advantages to combine DSC with MIPI DSI-2 transport. The reduction in bandwidth by 3 times typically allows you to cut the number of transport lanes in half. Also, if your application requires a frame buffer, you can also benefit from some really interesting RAM saving. All of this translates into cost saving, real estate reduction, lower I/O pin count, being able to operate your design at lower frequencies, which help with EMI, and get some really interesting power saving. Now, I'd like to turn it over to Joe Rodriguez from Rambus to discuss the DSI-2 controller.
Thanks, Alan. Let me provide a brief overview of the controllers, the heart of the subsystem we're discussing today. So Rambus is a leading provider of MIPI controller cores for CSI-2 and DSI-2. The standard fortunately allows us to span a very wide set of applications with DSI-2 host and peripheral controller cores. With over 10 years of MIPI experience, we have a proven solution for ASIC and FPGA markets and enjoy a very high rate of reuse amongst our customers. Our second generation MIPI IP added full support for C and D-PHY deployments with flexible 32 and 64-bit controller widths. They can support 1, 2, 3, 4 trios or D-PHY lanes. And part of our market success is the rapid deployment of the MIPI features, valuable off-the-shelf features. A prime example of this is the fully featured video interface. On occasion, this also means custom boot up configurations with bifurcation of the controller and the Mixel 5. Delivering a high-quality DSI-2 controller core, fully integrated with and verified with the Mixel C and D-PHY, is a vital service we provide and helps ensure uninterrupted customer silicon success. After integration and extensive validation of the PHY controller, the Hardent team validates the PHY controller DSC subsystem. With support for the DSI-2 v1.2, the Rambus controller is a solid foundation. The core's architecture allows customers to configure the IP deliveries for a specific application. For example, often VR teams may need a single trio, and desktop set needs support for 4 C or D-PHY lanes, implemented in a left, right, top or bottom display configuration. We engage with your design team to determine how to deploy the lightest IP delivery and meet your project requirements. Let me offer a bit more detail. The C-PHY is defined as a 16-bit PPI, analog to digital interface. If your bandwidth requirements are satisfied with the 2 trio, we can deploy that with a 32-bit controller core. Lowering gate count and power consumption and meeting the performance of your design requirements are becoming much more valuable as multi-instance architectures flourish in the market. For many design teams, having an FPGA prototype for rapid design proof of concept is required. We can provide off-the-shelf D-PHY solutions for Intel PSG devices or Xilinx devices. The DSI-2 video interface is traditionally deployed in environments where legacy display systems exist, where V and H-Sync support is required. This support has evolved due to customer requirements. The DPI-2 video interface defines the base functionality of our video interface. Our DSI-2 customers required support for more than the RGB 16, 18, and 24-bit data formats defined by the standard. The Rambus DSI-2 video interface adds support for all the data formats and extends the pixels per clock available, so the high-end markets can take advantage of this extended support. And after several DSC deployments with Hardent, it was apparent that this video interface and our native packet interface were a natural part of the DSC controller integration. And today we support this integration for our host and controller cores, and of course with either our 32-bit width or 64-bit cores. Now let me introduce my MIPI colleague, Justin Endo from Mixel.
Thanks, Joe. I'm Justin with Mixel, and today I'll be talking to you about the Mixel MIPI C-PHY D-PHY combo IP. So Mixel was founded over 20 years ago, and while we offered quite a few different IPs at the beginning of our company's history, we shifted our focus to the MIPI interfaces in 2006 when we joined the MIPI Alliance. Since then, we've been an industry leader of the MIPI PHY interfaces. So these would be your MIPI D-PHY, C-PHY, and M-PHY. We also offer an LVDS SerDes and a couple multi-standard SerDes, including an LVDS D-PHY combo and the IP we're discussing today, the C-PHY D-PHY combo IP. We offer a complete integrated solution, which includes the PHY, the controller from Rambus, the compression from Hardent, and an FPGA platform, which helps our customers reduce their time to market. Mixel was the first IP provider to demonstrate silicon-proven D-PHY, C-PHY, and M-PHY, and we believe we have the widest coverage of process nodes and foundries in the industry. We're silicon-proven in 11 different nodes and at 8 different foundries. So while Elaine and Joe alluded to this earlier, I want to highlight a bit more about MIPI PHYs in general and their target applications. So MIPI PHYs target those kinds of applications that require low power, high bandwidth in a minimal area. So these include mobile as well as mobile adjacent applications such as automotive, IoT and sensor or edge processing, virtual reality, augmented reality, and mixed reality, and other consumer electronics. So let's spend a little bit of time here on the Mixel MIPI C-PHY D-PHY combo IP itself. This combo PHY can be configured for either D-PHY or C-PHY, as the name suggests, and gives added flexibility as D-PHY is still much more prolific in the market, while C-PHY has been gaining wider adoption and provides some extra bandwidth when needed. And this combination PHY helps extend the life cycle of our customers' products. Here we're looking at the universal configuration, which is a superset with all the sub-blocks for both transmit and receive modes. The IP in the main subsystem block that we were looking at earlier, and we'll look at again later, is an area-optimized DSI transmitter version of this IP. The universal configuration itself supports both CSI-2 and DSI-2. Now the D-PHY here is compliant with the version 2.5 version of the specification and reaches 4.5 gigabits per second per lane with 18 gigabits per second aggregate bandwidth with 4 lanes. And the C-PHY is version 2.0 compliant, reaches a speed of 4.5 gigasymbols per second per trio and with 3 trios reaching an aggregate speed of over 30 gigs. Now with the Mixel Rambus Hardent Display Subsystem solution, you can achieve 3 times the base bandwidth. So because of this, and depending on your target application, you may not need all 3 trios and 4 lanes. So in that case, a 1 or 2 lane or 1 or 2 trio version would also be available and can result in some big area savings. The IP itself is made up of 2 portions, the hard macro and soft macro. The hard macro on the right is delivered as a GDS, and the soft macro is a control interface logic, which is delivered as an RTL to be synthesized by the customer with Mixel support. Area overhead is minimized by reusing all of the D-PHY blocks for C-PHY operation and sharing of all of the serial interface pins. And while this is a universal configuration, we also offer full-speed internal loopback testability with minimal area overhead for high-volume manufacturer testing with our proprietary TX Plus and patented RX Plus configurations. Now, MIPI D-PHY version 2.5 and MIPI C-PHY version 2.0 includes additional features that weren't available in previous versions of the specifications, such as spread spectrum clocking, or SSC, and transmit equalization de-emphasis. New power-saving functionality, such as high-speed TX half-swing mode and high-speed unterminated mode, as well as support for the new alternate low-power mode, which is suitable for IoT applications with long channels, enabling fast bus turnaround. So this is a very mature IP with multiple generations, and you can see some nice eye diagrams here for some of the latest silicon-proven versions. Now, one point of differentiation for Mixel is our design approach, which we call a logarithmic approach, or a modular design approach, allows us to dramatically reduce the time to port and minimizes risks. We have a saying around here that first-time success is the rule, no exceptions, and we don't take this lightly. And for all generations, iterations, and ports of our IP, this has been our track record. And with that, I will pass it back to Elaine, who will discuss more about some of the target use cases of our combined display subsystem. Thanks, and see you soon.
Thanks, Justin. Let's take a look at some real-life use cases starting with mobiles. Mobile display requirements have evolved significantly over the past few years. High-end mobiles now need to be XR ready and capable of gaming, which command higher frame rate like 120 frames per second. There is also a movement toward OLED, which has several repercussions. It is now common to see DDIC frame buffer well over 100 megabit. Effectively, all these developments mean that over the last 10 years, display bandwidth has increased by 23x fold, while display interface PHY has only increased by 4 to 5 times. So high-end mobile can only be made possible with the use of visually lossless compression. It is very common now to find DSC encoder inside mobile application processors and DSC decoder inside the DDIC that belongs in the display module. Here are 2 tables that summarize the number of DSI lanes required for 2 different PHY speed, version 1.1 at 1.5 gigabit per second per lane on the top, and version 1.2 of D-PHY at 2.5 gigabit per second per lane on the bottom. And in the column, you see different display resolution. So you can really see the benefit in terms of lane saving, especially for higher display resolution. So for example, in the case of 2400 by 3840, if you don't have compression, you would have even more than 8 lanes. And fortunately, with DSC compression at 3x, you're down to 4 lanes. In the case of D-PHY 1.2, you would go from uncompressed at 8 lanes down to 3 lanes using 3x compression. So there are clear benefits for using DSC for those kind of applications. In the XR market, we can generalize the product to 2 different types. First is the tethered products, where the HMD, the head-mounted display, is connected over a cable to a game console. And then there's the second type, the wireless products, where there are even more challenges, power consumption and physical size being very limited. Here we are showing you how an AR wireless head-mounted display would look like with the IP subsystem from our 3 company that you see in the diagram over there. So the use of DSC in the XR product also provides additional benefits by reducing the memory buffer size and bandwidth, which leads to smaller footprint, smaller cost, and significant power saving. So while keeping extremely low latency, which is very important for this type of application. And finally, let's talk about our last use case today, automotive applications. Car displays and camera requirements are evolving very quickly, and so are the transport bandwidth requirements. Number of displays and cameras in a car is radically increasing. More video sources and display mean more cables. Car makers are typically very sensitive to the number of cables and wires, as they lead to an increase in weight and manufacturing cost. So car makers are prepared to spend a little bit more on the semiconductor side to make some copper savings, and so this is where the use of compression comes very useful. With the proper architecture, it is possible to significantly reduce the number of cables inside a car. Essentially, it consists of having an architecture where each source and sync devices, whether they are GPUs, application processors, or displays, are equipped with DSC-compatible video encoders and decoders. This way, many video streams can be transported inside the car with a significantly reduced number of cables. Now that you've heard about each of the IP blocks, let's take a look at how they all come together in our integrated IP solution. So here's the block diagram of the DSC encoder, MIPI DSI-2 controller, and the C-Combo D-PHY integrated solution. So this is an IP subsystem designed to enable video transmission over the C and D-PHY combo. This subsystem includes support for DSC compression over the MIPI DSI-2 transport. So the pixel source on the left side of the diagram can be asynchronous from a DMA engine or synchronous from a timing reference. So both compressed path as well as uncompressed path can be supported. So this is a full dual link implementation of the MIPI DSI-2 subsystem. A single link is also a solution possible, as illustrated by the dotted lines in the diagram. So you see the dual link over there. The DSC encoder implements a fully compliant version of the VESA DSC 1.2 compression. The IP compressed the video input to reduce the DSI link bandwidth requirement. The DSI-2 host controller has been tightly integrated with the DSC encoder, and the integrated solution minimizes the overall static RAM requirement as well as power consumption. The integrated solution is delivered to customer with a complete set of deliverables for each IP included, as well as the top-level integration code that has been fully verified. So to summarize, there are many benefits to using this integrated IP solution. The IP have been adapted and tightly integrated together to render the best possible solution. So with this subsystem, you can benefit from lowering your project risk with a fully integrated and verified solution. You can maximize the functionality and availability of all the MIPI DSI-2 operating modes. It's optimized for ASIC design performance with, optimized PPA. You can accelerate your project schedule for your ASIC or SoC project as the solution is immediately available. And you can benefit from the extensive expertise of each of our company in their respective field. If you would like to see a working demo of our IP subsystem, please tune to the Mixel demo at 8:05 Pacific time this morning. If you want to find out more information, here's our contact information. Thanks for listening to our presentation today. And with that, let's take some of your questions. Thank you.